Welcome to the course Introduction to Algorithm. My name is Sourav Mukhopadhyay. I am a faculty member at IIT Kharagpur. I am lecturing this course. This is lecture 2 of this course, and in this lecture we will be discussing how to solve the recurrences. So, let us just recap what we did in the lecture 1. So, lecture 1 we have discussed two sorting algorithms, namely insertion sort and merge sort, and we analyze those algorithms. So, we talk about their time complexity, the run time, and there we discuss the asymptotic notion of time complexity, and we have seen the insertion sort is order of n square algorithm in the worst case, whereas merge sort is order of n log n algorithm in the worst case. But insertion sort is merge sort is not a in place sorting algorithm. That means merge sort, we have given an array to sort, we need to take an extra array of same size to in this merge sort code. But whereas in insertion sort, it is an in place sorting algorithm. That means everything we are doing in the same array. So, we do not need to take help of any extra array or to sort that. So, in this lecture we will be discussing how to solve the recurrences. Okay, so as I said, in the lecture 1 we have discussed the merge sort, and while analyzing the merge sort we got this type of relation in the time complexity, where Tn is the time complexity of the merge sort, where the input size is n, where the n element need to be sorted. So, this was the this is the time for merge sort, input size is n, and we got this recurrence. This is called recurrence. We got the relation of the time complexity like this in this form for merge sort. Now, the question is how we get the solution of this recurrence. That means this is okay, this is a relation, but we want to know whether this is the order of n square algorithm or order of n log n algorithm. So, who can give us that? So, that means we need to solve this recurrence. So, this lecture is all about that, how to solve the recurrence. So, we have seen one method of solving the recurrence in the last lecture, which is recursive tree method. So, that we will discuss again in this lecture, and apart from that we will discuss two more methods for solving the recurrence. One is this substitution method, which is most general method, and then again the recursive tree method we will recap, and then we will go for the master method. Master method is the more powerful method, which the most of the common recurrence can be solved by master method. So, we usually get the recurrence from any algorithm. Any algorithm will give us the time in a recurrence form, and then it is necessary to solve those recurrence. Okay, so let us start with the first method, which is substitution method to solving the recurrence. So, substitution method is basically has two steps. One is we need to given a recurrence, we need to guess the solution, whether it is order of n square, whether it is order of n log n, or whether it is order of n cube. So, we first guess the solution, and then we need to verify our guess by the mathematical induction. So, we need to prove that our guess is true. Now, if we recap, mathematical induction means we have a property in terms of n, because Tn is the time complexity. We want to show Tn is order of n square. So, this is a property in n. So, we need to show this is for all n. So, just I am recapping what do we mean by mathematical induction method. Mathematical induction method means we have a property in property P with n. This P is a property with n, where n is the natural number. So, mathematical induction method is telling. Now, if we assume, that is the induction hypothesis step, if we assume there are three steps in this method. If we assume that this method is true for up to n, and if we can show this method is true for n, that means if this method is true for up to n, and if we can show this method is true for this property, method means this property P, this property is true for n, and if we can have a base case that P is, this property is true for 1 or 2, some base case if we can achieve, then we can claim that this method is true for all n after this base value. Okay, that is what do you mean by mathematical induction. So, we will use that mathematical induction proof to verify our guess. So, let us take an example. So, suppose we have given this recurrence Tn is equal to 4 Tn by 2 plus n. Now, suppose we have to guess the solution for substitution method. Now, suppose we are guessing this is a big O of n cube algorithm. So, this solution of this recurrence is big O of n cube. So, Tn is big O of n cube. So, now we will use the mathematical induction to verify our guess whether we are correct or not. So, for that we assume that this is true for up to, so this is true for up to n. So, big O of n cube means it is less than equal to some constant into that cube. So, Tk, so Tk is basically big O of k cube. So, Tk is basically big O of k cube. Okay, and this is true for up to n. So, that means Tk is less than c k cube, that is what do you mean by definition of big O. And now we need to, this is the induction hypothesis, this is the assumption, this is induction hypothesis or the assumption. And now we need to prove that this is true for n. That means we need to show Tn is less than Cn cube. So, that we will try to show. If we can show that, then it is true for all n after the base value. So, then we can claim that it is order of n cube algorithm, I mean big O of n cube algorithm. Okay, how to show that? So, we have the recurrence Tn is 4 Tn by 2 plus n. So, which is basically 4, now this n by 2 is k, now n by 2 is less than n. So, we can use the assumption induction hypothesis. So, this is less than c k cube. So, that will give us less than 4 c n by 2 cube plus n. So, if you simplify this, it is c by 2 n cube plus n. Now, we want to show this is less than equal to c n cube. That means, we want to write this c n cube minus some term, and that term need to be positive in order to achieve this is less than c n cube. So, this term will be positive if we choose c to be greater than equal to 2. C is a positive constant, we can play with c. So, and this is true for all n greater than equal to 1, n is a natural number. So, that means this proves that this is true for n. So, that means Tn is order of n cube algorithm. Now, the question is whether we can make a tighter bound on that. I mean, whether the we can guess that Tn is order of, I mean big O of n square or not. So, for that let us try. So, now we want to try whether this Tn is order of n square or not. So, this is our guess. So, we are guessing that Tn is order of, I mean big O of n square. So, for that this is the definition. So, this is our induction hypothesis. We assume that Tk is also big O of k square. So, that means Tk is less than Ck square for all k less than equal to n, and then we have to show this is less than Tn is less than Ck square. Let us try that. So, Tn is this is the recurrence, and now this if we simplify, this is n by 2 must be less than n by 2 square. So, n by 2 square, here is a mistake over here. So, this will be n square by 4. So, this will cancel out. So, it will be Cn square plus, sorry. So, this will be so this will be Cn square plus n. So, plus n, that cannot be less than Cn square, because this has to be positive, but this is minus n. Minus n cannot be positive because n is a natural number. So, no choice of C will give us this is less than Cn square. So, that means by this way we cannot show this is a Tn is less than Cn square. So, that means by this way we cannot achieve that Tn is big O of n square. So we lose, or is there any other way to show that? Yes, because order of n square or order of k square means we can take we can strengthen the bound, we can take the lower order term for our health. So, that we will do in the next slide. So, we strengthen the induction hypothesis by taking the lower order term, because that is also, if we take this is C1 k square minus C2 k, that is, if we ignore lower order term, that is basically order of k square. So, we assume that this is Tk is less than equal to C1 k square minus C2 k for all k less than n, and if we can show that Tn is less than C1 n square minus C2 n, then we are done. So, that we are trying to achieve. So, Tn, this is the recurrence, Tn is 4 Tn by 2 plus n. Now, this n by 2 is our k, which is less than n. So, we can use this induction hypothesis. So, if you put that, it is less than equal to 4 into C1 n by 2 square minus C2 n by 2, and then here one bracket is missing, and then we have, if we simplify this, it is C1 n square minus 2 C2 n plus n, and this we want to show less than equal to C1 n square minus C2 n. So, this we want to write C1 n square minus C2 n minus some term, and this term has to be positive, and this is C2 n minus n, and n is greater than 1. So, this will be positive if we choose C2 to be greater than 1, and that is always we can do, because C1 C2 are the constant we can play with, positive constant. So, this is the so this way we can, if we strengthen the bound this induction hypothesis, then we achieve that this is a big O of n square, solution is the big O of n square. Now, we can I give this exercise to you. You try to show this Tn is big omega of n square. Okay. This is big omega of n square. This is n, sorry. This Tn is big omega of n square. To show this, what we have to, we will use the same method, substitution method. We just instead of less than equal to, we will use the greater than equal to. If we need to strengthen the induction hypothesis, that we will try. So, this is true. So, Tn is big omega of n square. So, we have seen this is big O of n square, and also as an exercise you can prove this is big omega of n square. So, together we can say this is a big theta of n square. So, solution, this solution is big theta of n square. So, big theta means big omega and big O. So, big theta of n square. Okay. So, this is what is called substitution method, and it is a foolproof method. It is more general method because it has a mathematical proof behind this. So, the next we will discuss the recursive tree method, which we have already introduced in the lecture 1 when we get the time complexity of March sort. So, recursive tree model we have we have seen in the March sort. So, there this recursive tree model will help us to guess the solution, because for substitution method we need to guess the solution. Okay. So, that from where we can get this intuition, what is the solution. So, that recursive tree method can give us. Okay. So, it is a good idea to guess the solution. So, let us take an example of a recurrence which we are going to solve using the recursive tree method. So, suppose this is a given recurrence, Tn is equal to Tn by 4 plus Tn by 2 plus n square. So, we have suppose we have an algorithm which gives us this type of recurrence in their time complexity in Tn. So, now we need to solve it. So, basically this type of thing we can achieve by divide and conquer technique, which is similar to merge sort. So basically divide and conquer, we have a problem of size n, this we are dividing into two sub problems, n by 4, n by 2, and this is the cost for combining, I mean merging. In the merge sort it was merge cost, that was order of n, but this could be different. So this may be some other algorithm we can get this type of recurrence. So let us solve this, let us draw the recursive tree to solve this. Okay. So this is Tn, so Tn is divided into two sub problems, n by 4, n by 2, and we recursively solve this sub problem, this is the cost for this, this is the cost for this, and this is the cost for when we have a solution for this, this is the cost to combine these two. So the total cost Tn is sum of all this, so that is the Tn, Tn is equal to T of n by 4 plus Tn n by 2 plus. Now this is a problem of size n by 4, so this again we can subdivide like we did for merge sort, n by 2, then again n by 4, like this. So that we will do, that is the basically recursive tree. So if we do that, then that n by 4 will divide into, we will use the same recurrence. So we will put just n by 4 instead of n, so it will be n by 16, this will be n by 8, and this is the n by 4 square. So this is the cost for combining. So similarly here it was n by 2, it will divide into, just put n is equal to n by 2, it will be n by Tn by 8, and this is Tn by 4, and this is n by 2, Tn by 2. So we will continue like this until we reach to a 1, because when we reach to a 1, every problem need to be stopped. Any problem, if it is sorting problem, 1 means already sorted, one element is sorted, then we can come back. So like that we did it in merge sort. So this is this will continue until we reach to a 1. So so total cost is the sum of this all. Okay, now how to get the sum? So the total Tn is the sum of all these nodes, this plus this plus this plus this plus all the nodes, this whole tree. So how to get the sum? We can get the sum by calculating the level wise sum. So this level it is n square. So next level it is, if we do it, 5 by 16 n square, and this level if we calculate we will get 5 by 16 square n square. Like this it will continue. Okay. So now the solution is sum of all this. So if we take the n square common, it will be 1 plus 5 by 16 plus 5 by 16 square plus 5 by 16 cube, like this. So in the ith level it will be 5 by 16 to the power I n square. So but that needs a proof. It is not a, so by this method we can say it is a general method, because we are not proving that ith level it will be 5 by 16 I to the power I. That needs a proof. For that also we can use the mathematical induction. So that's why this recursive tree will give us the will help us this intuition to guess the solution. So this is the time for this n square. So if you sum all this, so n square we take common, and this is basically the geometric series, and it's up to finite term, but if you make it infinite, this is less than equal to this, and this is basically 1 plus r square. We have this 1 plus r square dot 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 up to infinity. So this is basically the sum is, if r is less than 1, it is 1 by 1 minus r. So that is less than equal to that. So this is basically r is 1 by 15. So that will contribute in 1 by 1 minus r is 5 by 16. So 1 by 1 minus 5 by 16. So that is just a constant. So it is basically big theta of n square. Again we can show it. This is a big omega of n square, big O of n square, big omega of n square. So it is a big theta of n square. So this is the recursive tree method. But it needs a proof that why this is ith level it will be 5 by 16 to the power I. So, that is why we are telling this method is for the intuitive method for doing that. Okay, so now we start with the master method. So, in master method we have this type of recurrence, Fn t of n is equal to a t n by b plus f of n. So, master method can solve this type of recurrence. The recurrence would be in this form, then we can try to get the solution by using master method. So, where is a is greater than equal to 1 and b is greater than 1 and f is a positive function. Asymptotically positive means f n is greater than 0 for all n after some n 0. So, basically for large n f n is always positive. So, the question is how we can get this type of recurrence from which type of algorithm. So, we have seen one this type of recurrence is coming from the merge sort. So, merge sort, if we recall, the recurrence was T n equal to T of n equal to 2 T n by 2, 2 T n by 2 plus f of n plus c of n plus theta of n or c of n or n. So, this is of this type. Here a is 2, b is also 2 and f n is this. So, this type of recurrence we can get directly from the divide and conquer approach. The merge sort is one example of divide and conquer approach, where we have a given problem of size n. Here in the merge sort we have a sorting problem. So, we have a array of size n need to be sorted. So, we divide the array into two sub array, each equal size n by 2 n by 2. Then we recursively sort these two sub array and we combine, we merge this with this cost to get the whole sorted array. After recursively solving these two sub array, once we have a sorted two sub array, then this is the cost to merge them. So, similarly for other divide and conquer technique also we have this type of recurrence. Suppose we have a problem of size n, we divide the problem into a sub problems. So, a is the number of sub problems and then the size of each sub problems is n by b. So, here we have two sub problems and size is half, but in some scenario we can get the size is n by b sub problems, and this is the cost for merging or combining. So, we have a solution of all the sub problems and then this is the cost for merging this sub problem. So, we have a n over here. So, n is dividing into many sub problems, many sub problems, and each of size of each sub problem is coming out to be n by b, each of these. So, how many of them? There are a. So, we divide this problem into a many sub problems, each of size n by b, and then the divide and conquer technique is telling us we recursively solve all these sub problems. We are recursively solving all these a sub problems and that will cost us this, and then this is the cost for f of n, this will be f of n. So, f of n, if this is t of n by b, f of n will be the cost for combining. Okay. So, that is the form for the master method. So, if our recurrence is of this form, then we can try to solve it by using, we can try to apply the master method, where we have this type of parameters are like this, a is greater than equal to 0, because we should have one or more sub problems, and then b is greater than 1, that means we should reduce the problem into lesser size. So, that is the meaning of b is greater than 1, and f n is the cost for combining or merging and cost is positive. So, that is the way. Okay. So, the master method, there are three cases of master method. These are the three common cases of master method. So, cases are coming by comparing two terms. This is f n and this is n to the power log a base b. So, these two terms will compare. So, when you compare two terms, then there are three cases, three possibilities will occur. One is bigger. If suppose this is a term, this is b term, the case 1 is a is more, I mean case 1 is Fn is slower. So, case 1 is this is less than this, case 2 is these two are equal, I mean equal slower we will discuss in a proper way. But there are three cases, one is less, one is these two are equal, and third one is greater. So, based on these two value we will compare. So, what is these two values? Basically these two values are coming from this is the cost for combining. Once we have a solution for the sub problems, and this is the cost for the timing, we can assume this is the cost for recursively solving those sub problems. So, this is the cost for recursively solving those sub problems. We will have a recursive tree for master for this recurrence, then this will be more clear. But intuitively just think about this term. This term is the n to the power log a base b. So, this term is the time complexity or the run time, how much time we are spending in recursively solving those sub problems. And this is the term Fn is once we have a solution, once we get the solution of the sub problems, how much time we are, what is the time for merging those, I mean combining those. So, once we have a solution from here, so now whichever is the dominating, so that will be the total cost. So, total cost should be this recursively solving those sub problems and then the combining cost. But if one is very big, say this is 100 and this is 5, then asymptotic sense, this is big, then it will be the run time. So, that way we will have three cases. So, which cost is dominating, whether the this cost, this is the cost for recursively solving those sub problems, or this is the combining or the merging cost. So, these two term will compare and we will get three cases of the master method. So, let us talk about the first case. The first case is telling us this Fn is slower, that means we are spending more time in recursively solving this. So, this is faster, this is more. So, this is more, but how will quantify, I mean how will say one term is more, because these are all sort of a function in n. So, how will measure one term is more? So, this is the one way to measure one term is more. We will say Fn is slower than this. So, we will say Fn goes polynomically slower than n to the power log a base b. So, this is slower. How slower? If we multiply, if we divide this by a polynomial factor, then also this Fn is slower. So, that means if we take this n to the power log a base b, this is dominating, this is more, n to the power log a base b, we want this to be more, a base b. So, now this is dominating, so this is big, this growth is faster. So, how faster? Polynomically faster, that is Fn is polynomically slower. That means what? If we divide this term by a polynomial factor n to the power epsilon, epsilon is greater than 0, epsilon could be 1, 2. So, if epsilon is 1, this is n to the n, and epsilon is 2, this is n square like this. So, this is a polynomial term. So, if we divide this by a polynomial term, then also Fn is less. So, this become, so just we can erase this. So, this is, yeah. So, Fn is lesser than this. So, Fn is less than some constant fraction of this c into this. So, this is nothing but this big O of this, because this is what? This is c into n to the power log a base b minus epsilon. So, that means Fn is less than constant factor into this term. So, that is the notation we use for asymptotic notation. Is that if we recall from the first lecture, asymptotic definition of the definition of this asymptotic notation, big O of some Gn. So, that means Fn is big O of belongs to big O of this. So, Fn is slower. How slower? This is more. How big this is? Even if we divide this by a polynomial factor, then also Fn is less than that. So, that means this is the dominating thing. So, obviously the runtime will be the cost which is dominating. So, runtime will be theta of n to the power log a base b, the time which we are spending in recursively solving these sub problems. Okay, because this time merging time is very less compared to the other recursively this time. So, this is the runtime then, because this is more, say this is 1000 and this is just 5 seconds. So, there obviously 1000 is the runtime, 5 seconds is negligible in that sense. So, this is the first case. So, first case is Fn is less. I mean less means we have to quantify this. This is the way we quantify this. Fn grows polynomically slower than n to the power log a base b. So, that means if we divide this by a polynomial factor n to the power epsilon, then also Fn is less. So, Fn is less than some constant c into this, and this is nothing but this, and this is the notation we know big O of this term. Then the solution is this. So, this is the case 1. Okay, sorry. Now we can remove this. So, now we go for the case 2. So, in the case 2, the both are same. So, if we are comparing two terms, there are three possibilities. One is big, one is less, one is big, one is equal, that is the case 2, and one is one is less. So, sorry, less, equal and more. So, this is the three possibilities there. So, this case we have Fn is Fn and this thing n to the power log a base b, they are similar. Similar means their growth is similar. So, that means Fn and n to the power log base b, they are similar, or they can differ by a log factor. So, if we see here, they are similar means if k is equal to 0. So, this is a big theta, means bounded both sides. So, if k is equal to 0, then this term won't be there. Then we have only Fn equal to big theta of n to the power log a base b. So, in that case, what we have? In that case, we have C1 n to the power log a base b log a base b less than equal to Fn, which is less than equal to some C2. This is the big theta notation, we know the definition, n to the power log a base b. So, that means their growth is similar. I mean Fn is bounded both sides by n to the power log a base b. So, their value is same, they are having the same growth. Okay, so, growth is similar. So, this is when k is equal to 0. If k is not 0, suppose k is 1, then they are varying by a log factor, log n factor. So, log, this is base 2, this is Lg, Lg means base 2. So, it is very less compared to n. So, they may be exactly similar, their growth may be exactly similar, or they may vary by a log factor or power of log factor. If k is 2, then it is log n square. If k is 3, log n cube. Okay. So, they are very much similar. So, in that case, what is the solution? The solution is Tn is equal to big theta of n to the power log a base b, then this, due to this log factor, it is log k plus 1 n log n base 2 here to the power k plus 1. So, even if k is equal to 0, we get a log factor over here, because we will see when we give the rough idea of the proof, when we draw the recursive tree. So, the height will be this much, and each label we have similar cost, because they are similar. So, the total cost will be this into log n. So, when they are exactly similar. So, that we will discuss, but this is the solution for case 2, and case 2 will occur if Fn and n to the power log a base b, their growth is similar, or they may vary at most by a log factor or power of log factor. Okay. So, this is case 2 of master method, and we will take some example after this. We have another case, which is case 3. So, case 3 is, so we have seen Fn is slower, we have seen Fn and n to the power log a base b, they are similar. Now, Fn is faster, Fn is more. So, that is the third case, or case 3 of master method. So, in the third case, how, so we have to quantify how big this is, how faster, I mean this Fn is more now, Fn is the dominating things. So, how more, I mean we need to quantify this, how big. So, this is the way we can quantify. Fn grows polynomically faster than this. That means, if we let us, if we have n to the power log a base b, n to the power log a base b, okay, sorry, this is a. If we multiply this with a polynomial factor n to the power epsilon, so that is basically this one, n to the power log a base b plus epsilon, then also Fn is more. So, Fn is greater than equal to some constant into this, and that is nothing but the big omega notation. If you recall the definition from the lecture 1, this is big omega notation, and epsilon is greater than 0. So, epsilon could be 1, 2. So, this is a polynomial factor. So, Fn is faster than n to the power log a base b. So, Fn is the dominating cost, the combining cost at the top, that is the dominating cost, and that is very heavy. So, then we have, this is one condition, and in this third case we have another condition. You have to really see, this is a double checking, you can say that really Fn is the dominating, I mean Fn is more than the other level of the recursive, if we draw the recursive tree, then it will be more clear. So, that is the regularity condition. What is this condition is telling? So, to understand this condition, let us draw the recursive tree of this. So, we have this Fn, this is the combining cost, and then it is, so initially it was Tn, and it is dividing into a many sub problems. Sorry, this is, it is dividing into a many sub problems, and each of size a many sub problems, and each of size n by b. So, this is Tn and this is Tn, Tn will be T of n by b. So, again if we divide that, it will be f of n by b. So, that will be the cost for combining in that sub problems, n by b, and we have further have the term over here a many. So, this is all f of n by b. So, at this level the total cost is a of a into sorry, this is should have a proper a. So, this is the cost a into this level. Everything is f of n by b. So, there are a many. So, at this level the cost is f of, this is again not epsilon. So, we can just draw a better f over here. So, this is f of, this is f of n by b. Okay. And we have the lower term also. So, this level cost is f n and this level cost is a into f of n by b. So, we want f n is the dominating cost than all the levels. So, we want f n is the heavyweight guy. So, f n should be much more than this. So, that means this is less than by a constant fraction of this. So, that is the regularity condition. So, this guy, this a of f n by b, which is the cost at the next level, this should be strictly this should be less than equal to some constant c. This is a fraction. This should be less than fraction of this guy. So, that is the one another. I mean, this is a double checking, you can say, to quantify that this is the dominating cost. So, this is the extra condition for the third case. So, third case we have to check this condition, and this must be, we should have a c such that this thing happening a f of n by b must be less than c of this. So, in that case, what is the solution? Solution is obviously the cost of this cost, because this is the dominating cost. When we are comparing these two, this is the heavyweight guy. So, the runtime will be this, I mean, this growth is much more faster than this growth. So, this is the runtime for case 3. But we have to remember that we have to check these regularity conditions. Okay. So, now we will take few example and we will see how we can apply the master method, and then it will be more clear. Okay. So, let us take the first example. Suppose we have given this recurrence T n is equal to 4 T n by b plus n, and we can check these recurrences of this form. This is the typical form of the master method. So, here what is A? A is 4, what is B? B is 2, and what is f n? F n is n. So, now we calculate n to the power log A base b. N to the power log A base b is basically here A is 2. So, sorry, A is 4, B is 2. So, it is coming 2 square, then 2 square log 2 square base 2. So, it is 2 is coming. So, n square. So, it is n square. So, n to the power log A base b is n square, and f n is n. So, who is dominating? Who is more? So, this n square is more, and it is polynomically more. So, that means if we divide this by n square divided this by n, then also it is less than some constant into this. So, this is the mathematical way we can see that f n is polynomically slower than n to the power log A base b. But from here we can easily say that n to the power log A base b n square, and this is n. So, n square is much more. So, the cost runtime should be n square. So, T n is big theta of n square. This is the solution for this using master method. So, this is case 1. Okay. So, now come to the another example. Say the same one, I mean the T n is 4 T n by 2 plus n square. Instead of n, we have n square. So, this is this recurrence is of this form. A is 4, B is 2, and again we calculate n to the power log A base b. This is n square, and f n is here also n square. So, these two are similar. They are similar growth. So, they are same or similar. polynomically similar, or they are, and we, so case 2 and here they are exactly similar. So, there is no log factor over here. So, we have this case 2, this falls under case 2 of master method where k is equal to 0. So, if you recall the case 2, this is the case 2 of master method where we have a log factor, but here they are exactly similar. So, we have k is equal to 0 over here, and then this is log means base 2. Then we have a solution big theta of n to the power log a base b into this k is 0 means we have only log n. So, that is the solution for case 2. So, the solution for this example will be k is equal to 0. So, solution will be n square, that is n to the power log a base b into log of that k plus 1 power. So, that is log n. So, this is the solution for this recurrence, and this falls under case 2. Even if we have a log n over here, then k will be equal to 1. Suppose we take another example, say Tn is equal to 4Tn by 2 plus n square into log n, I mean log n base 2. Then k will be 1 and the solution will be log n square here, I mean n square log n square. Now, this case 2, if we recall the Marshall recurrence is Tn is equal to Tn is equal to 2T n by 2 plus Cn or theta of n. Okay. So, now we can use this, this is of this form of master method. So, we can compare these two, this is of this form. Now, we can get these values of a, b. So, a is 1, sorry, a is 2 and b is 1, sorry, b is also 2. So, what is n to the power log a base b over here? This is basically n. And what is Fn? Fn is also n or Cn. So, they are same, they are similar. So, their growth is same. So, here this is also case 2 with k is equal to 0. Then the solution is, we know the solution, Tn will be big theta of n to the power log a base b, that is n, and we have a log n over here for k is equal to 0. This log is base 2. That is exactly what is the solution for, what is the runtime for Mart sort. So, this Mart sort comes under case 2 of master method. Okay. So, we take another example over here. So, this is the another recurrence, Tn is equal to 4Tn by 2 plus n cube. So, this is also of this form, here a is 4, b is 2. So, if you calculate n to the power log a base b, it is n square, and Fn is basically n cube. So, this is faster. How fast? This is polynomically faster, because if we multiply with n to the power epsilon with this n square, then also it is more. So, Fn is greater than equal to some constant into this, where epsilon is equal to 1. So, that is basically big omega naught. A compact way we can write this, but basically this is polynomically faster than this. So, this is n cube, this is n square. So, but for case 3, this is not the only condition we should check. There is another condition which is called regularity condition we should check, and regularity condition was we should have we should see a of f of n, f of n by b. That was the cost at the next level. So this should be less than fn. So this should be less than some constant factor of fn. So this we have to check. So this was the regularity condition. So sorry, fn. This will be fn. This is just fn. So this was the this is the regularity condition we should check. Now we can do that. B is 2. So so what is this? Let us calculate this. So A is basically 4. So 4 into f of n by b. N b is 2. N by b is basically what? N by fn is n cube. So n cube by 8. Sorry, this should be 3. So this is n cube by 8. N cube divided by 8. So this must be less than equal to some c into n cube. Okay. This c won't be there. So 4 into n cube by 3, n cube by 8. This c won't be there. Sorry. So this should be less than equal to some c n cube. That c is c should be less than, we should get some c which is, so this is a fraction, we should get a c which is less than 1 greater than 0. So this will satisfy. So this is half. So for c, any value between half to 1, so if you take c half, this will satisfy. So any value of c between half to 1 will give us this. So this regularity condition is also satisfying for this case, for this. So this comes under case 3, where fn is the dominating cost. So the solution will be Tn is equal to big theta of fn. Fn is n cube. So this is the solution, and this is the this is case 3 of the master method. Okay. So let us erase this. Then we will take another example, and we will see which case that is coming. So there are basically 3 cases of master method, that is we know that is coming depending on the value, depending on the which one is the dominating cost, whether the recursively solving things is the dominating, or the merging or the combining cost is dominating. So that is the one. So let us take the another example, and we can see whether we can solve this by using master method. So suppose we have a recurrence like this, Tn is equal to 4Tn by 2 plus n square by divided by log n. So this log is base 2. Now this is of this form, no doubt. So we must try to solve this using master method. So a is 4 over here, b is 2. So n to the power log a base b is basically n square. Now what is fn? Fn is n square divided by log n. This log is base 2. Now which case this is coming? So if you see, this is between case 2 and case 3. This is not coming under any case. So here master method fails. So even though this recurrence is of this form, this master method cannot give us the solution for this recurrence. So sometimes it may fail. So this is one example where master method fails. So for another method is there, which is acrobacy method, which we will not discuss for this course. So that can solve this type of situation where master method fails. But that is out of this out of the scope of this course. We'll see mostly our recurrence whichever we will achieve, that can be solve using master method. So, those recurrence will fall under the 3 cases of this master method. Okay. So, now we will give the idea of the proof idea of master method. Okay. So, for master method, the recurrence is this: Tn is equal to AT n by B plus Fn. So, the proof will be proof idea is coming from the recursive tree. If you draw the recursive tree, so Tn is basically Tn is the time to execute the input size n, and this divided into a many sub problems, and each of lesser size, and each size of the sub problem is n by b. Then we solve these sub problems recursively to get the solution of the whole problem. So, that is the, so Tn is basically this is Tn is, so we have this Fn for merging or combining, and we have dot a many, and these are all sub problems of size n by b. These are all sub problems of size n by b, T of n by b. So, that is a typical divide and conquer runtime. So, we have a problem of size n, we divide this problem into a many sub problems, each of size this. So, Tn is basically sum of all this. Now, if we, now this is again a sub problems of size n by b. So, this again we want to further divide, and we put n is equal to n by b over here, and it will be this will be the cost for merging that particular sub problems, and then this will be T of n by b square like this, and we continue like this until we end up with a 1, because every algorithm should stop, that is the stopping condition of each recursive call at n is equal to 1. So, when n is equal to 1, we must stop. So, that is the stopping condition. So, the Tn is basically sum of all these terms. So, this is our Tn. So, this is the runtime for this algorithm. So, this is our Tn. So, Tn is basically sum of all this. Okay. Now, the question is how we will get the sum. So, Tn is sum of all this. So, now we have to do the level wise sum. So, first level it is Fn. So, second level it is f of n by b, a times f of n by b. Next level it is how many? This is a, and from here also we have a branch, from here each of these will give a branch. So, a square total. So, a square f of n by b square. So, if you continue like this, we have what is the height of this tree. So, height we can easily calculate, because this is coming to be n by b square. So, it is coming out to be 1. So, height is basically so height is coming like this. So, n by, if height is h, so n by b to the power h is 1. So, n is equal to b to the power h. So, h is log n base b. So, that is the height is coming. So, now how many leaps are there? A to the power h, because how many leaps means the number of nodes at the height level, at the h level. So, number of node in the first level is a, number of node in the second level, if you start with 0 level, this one a square. So, similarly number of node at h level is a to the power h. So, that is basically coming out a to the power log, that is the n to the power log a base b, and that is the cost at this level. So, this is the time at this level, how much you are spending recursively solving. So, this is the time at this level, how much you are spending. So, now the case 1 is coming, this is more time, the weight increases geometrically from the root to the leaf, and the leaf hold the constant fraction of the total weight. So, this is more, in the case 1 this is more. So, these are all negligible in that sense. So, weight is increasing geometrically. So, this is very, so this is the heavy weight term. So, that's why it is coming out to be this is the runtime for case 1. And for case 2, all the level it is similar. Case 2 we can just think by taking k is equal to 0. For k is equal to 0, this all the level it is similar. So, say for all the level it is this much. So, Fn and these are similar. So, all the level their cost is this. So, what is the height? Height is this log n base b, and then so that what is the total cost? N to the power log a base b into log n base b, but this we can change the base by 2, because log n base b is equal to log n base 2 into log 2 base b. So, this log 2 base b will be treated as a constant. So, it can be shown at it is big theta of this. And the case 3 is, this is the heavy weight guy. So, the weight decreases geometrically from the root to the leaf. So, this is negligible, this is the heavy costs, and that is the, and even we have a regularity condition over here. Okay, so that is the rough idea of the proof of master method by the help of recursion tree. Okay, let us conclude this lecture. In this lecture, we have discussed how we can solve the recurrence, and recurrence we can get for many algorithms, March sort or many other algorithms also, divide and conquer algorithm and other algorithm. So, those recurrence how to solve, we have learned 3 methods: substitution method, which is most general method and which supports mathematical induction proof, and then that needs a guessing of the solution, and then that guessing can be achieved by the recursion tree method, which is intuition. And then we have seen the master method, which is very powerful method, because most of the recurrence which is divide and conquer based techniques comes under master method to give the solution. So, in the lecture 3 we will be talking about divide and conquer technique. We will discuss more details on this, and we will see some of the known problems can be seen using the divide and conquer technique. So, that we will discuss in the lecture 3. Thank you.